Welcome everyone. In this video we are going to find the two-dimensional rotation matrix to rotate a vector. So the thing that we are interested in is we have a coordinate system. Let's call the horizontal one x hat direction and the vertical one the y hat direction, and we have a vector we have a vector a. Okay, now let me hold on a second. Okay, we have vector a pointing to this point. It has coordinates x, y. We want to rotate this by an angle of theta in the counterclockwise direction, which is the conventional way that it is the conventional way. It is the positive direction of rotation. That's why I call it the conventional way. Anyways, we want to rotate it in the counterclockwise direction by an angle of theta. Let's say this is the theta that we're talking about, and we're going to end up with vector b. And it will have coordinates x, let's call it, I don't know, let's put like a little, what do we call it, like an apostrophe on top of it. Okay, so this is the new x and the new y. Okay, so in this case, what we are basically asking is we have x and y, and we want to transform them into the new coordinates. How do we do this though? How do we transform this? Of course, it's going to relate to theta. That is the one thing that the rotation matrix is going to do. It's going to rotate the vector by theta. And you might be saying, why are we talking about a matrix? Can't we just find the new coordinates in terms of the old coordinates? And we can, but if we can express this rotation in a matrix, it is more compact. That's mainly the reason why we're doing this. So what we want is, we're going to have a rotation matrix, let's call it R, and it's going to be depending on theta, R of theta. And then we have the vector a, and this is going to give us vector b. Okay, and don't think of this r as a scalar. Even though I don't put it like that, you could even, I've seen some people put like an arrow like that to express that it is a matrix that they're talking about, but it looks kind of funny, so I'm not going to put it. I don't want you guys to be laughing all the time throughout this video, okay? It is good to laugh sometimes, but not throughout the video, please. I'm not doing a stand-up here. Even though you can watch the video while standing up. Was that funny? I don't think so. Okay, anyways. So we want this. We want to find what r is in terms of theta. And the general form is going to be, we have xy. This is a vector if we are using matrices. We want this vector to transform into this vector. Okay? And by the way, we call this x prime and y prime. I was thinking about this, like how do we call this? They are x prime and y prime. Now that I thought about them, okay. We don't need to call them x with a little something on it. Okay, it is x prime and the other is y prime. Okay? I was thinking about it throughout the video, but I didn't make it obvious to you, I hope. Maybe I did, who knows. Okay, so we're going to have a matrix here. It is going to multiply with A, and we're going to have B. Now, what is the matrix going to look like? What are the dimensions going to be? Well, we can figure what it's going to be, because A is 2 by 1. That means it has 2 rows, 1 column. And B is also 2 by 1. It has 2 rows and 1 column. Now, if we are going to be able to define a matrix multiplication, we need that the number of columns of the first matrix is the same as the number of columns of, let's say it again. For a matrix multiplication, if we are multiplying two matrices, and the vector is a matrix, if we are multiplying two matrices, we need that the number of columns of the first vector is equal to the number of rows of the second vector. So maybe the first vector, which is, the first matrix, which is the rotation matrix, maybe it has n rows. It can be anything, we don't know. But we know that the number of columns should be 2, so that it matches up with the number of rows of the second matrix, which is vector A. And the matrix, and the vector is just a matrix with only one column, okay? You could also have a 3 by 1 matrix, which is going to be 3 coordinates, which is more realistic in our life. We see everything 3D, but we're just interested in the 2D case for this video. Okay, so did you get that? We need that the number of columns of the rotation matrix is 2, because that is the number of rows of A. And if we are going to multiply them in this order, we must have it like this. And also, n can't be anything. It should be some value, some specific value. It isn't that hard to guess. It needs to be 2. Why is that? Well, because again, when you multiply two matrices, if you have something like n by m and m by r, we already discussed that these two need to be the same. And I'm just giving knowledge here. I'm not really going into detail about why this has to be the case. This is not a linear algebra video, but trust me, this is the case. If you don't trust me, comment in the video, comment in the comment section. I will make a video about this and I will hopefully answer your concerns. Okay, so, and when we multiply these two, we get a matrix that is n by r. So looking at the result, we see that n should be 2. Otherwise, we can't get a matrix that is 2 by 1 as a result. And this is the case then, okay. But you might be asking, and you should be asking, hold on a second, I don't need to multiply like the rotation matrix with the vector. Why don't I switch the multiplication order? Maybe I want to do it like we have xy, and then we put the matrix here. Why not? You might be asking this. Let's see if it works. This is 2 by 1. And this is also 2 by 1. Okay? So what was the idea? Well, the idea was that we need this number, and let's say it n by m, and this number to be the same for a multiplication. So n is 1. Cool. And what about m? And let me also erase. Hold on a second. Okay. So n is 1. And what about m? Well, for m, looking at the result, it is 2 by 1. And we discussed that it needs to be, it's going to have the number of rows of the first vector and the number of columns of the second vector. Then this should be 1 by 1. And if this is 1 by 1, this is not a matrix, this is just a scalar. And if you multiply a vector with a scalar, you just scale it up or down. So you just, multiply each component with a number. And that doesn't create a rotation. What you do in this case is you maybe have A like this. Or it is like this. This wouldn't change the direction. So we can't have a multiplication in this order. The multiplication order is the one that we initially started with. It is this one, okay? So, we are seeing that mathematically we can maybe express it in terms of a matrix multiplication, but let's see if we can in fact do it. And spoiler alert, we will be able to do it. Let's start. So let's say that A has an angle alpha here, and don't worry, we won't encounter alpha in the final result. Let's write each coordinate in terms of the given things, given values. X. So what is x going to be? And also I realized something very important before doing this. Please understand that we are rotating vector A by theta. We are not rotating the coordinate system. What we are doing is not this. We are not doing this, okay? We have x hat, we have y hat, we have vector A. We don't change the coordinate, we will change the coordinates, but we don't change the place that A points to in the space. We only change the coordinate system. We rotate the coordinate system by theta, let's say. This is x prime hat, and perpendicular to it we have y prime hat. And this is theta. We rotated the coordinate system by theta, not the vector by theta. And now we're asking for the new coordinates in terms of theta. We are not doing this because why am I mentioning this? I am mentioning this because if we were to do this, and we can do this in a future video if you guys want, if we were to do this, we would get a very, very, very similar result to the one that we're going to get in this video. These two situations are different, and you can understand why they are different fundamentally. In this one, you are changing the vector. Now it points to a different point in the space. In this one, it still points to the same point in the space, in space, but you just change your reference frame. You change the coordinates that you're describing the vector. They are different. And even though they give very similar results, they still are different. I am saying this because, after like a month or two maybe, you come across a problem and you might think, oh, I solved this. This is the formula. Maybe you are remembering it wrong. Maybe you are confusing scenario 1 with the second scenario. Okay? They are not the same. They really give very similar results. That's why I am emphasizing this. Please don't make this mistake of thinking that the rotation matrix is the same for these two cases. They are not the same. Okay? Okay, this was a side note. This is an important side note, I think. Because honestly, as a confession, I was confusing this at some point. But when I realized this, I said, it makes perfect sense. They are not fundamentally the same thing. So they have different rotation matrices. And it is just a coincidence that the rotation matrices look very similar. But they are different still. Okay, enough said. So what is x? X is going to be the magnitude of A. So let's call it, I don't know, like this. Let's put it A, okay? Without the arrow on top, that is the magnitude. It is A cosine of alpha. What is Y? It is A sine of alpha. What is x prime? It is magnitude of B times cosine of theta, right? No, it is not that. What is it? It is alpha plus theta. This is the angle for beta, for B. That is the angle, that is alpha plus theta. So don't put cosine of theta. That is cosine of theta plus alpha. Or we can write it alpha plus theta. We are adding theta later, so let's write it like that. What about y prime? It is b sine of, you wouldn't say theta this time. It is, as you know, alpha plus theta. Cool. Now, we're going to open this expression. What does open mean, you might be asking? Well, before even doing that, I jump from place to place, but there is an important thing. We are just rotating. So, we want the rotation matrix such that the magnitude of the vector is conserved. We don't want the vector to change its magnitude. We're just changing the direction. We are just rotating it. So, A should be equal to B. We are requiring this. This is the kind of rotation that we are dealing with. We are only changing the direction, not the magnitude of the vector. So, the two magnitudes are equal. Which means we could have written A for these two. But you get the point. I'm not going to erase and write A. So what is x prime if we write it more explicitly? B. Well, what is the summation formula for cosine? It is, and I have a video about this. You can access it from the cards right now and also from the descriptions part. I also have a video for the summation formula for sine, and you can find it in the cards and also from the descriptions part. So I have the proofs for this, okay? Don't take them for granted. Please go ahead, try to do the derivation on your own, and you can also check it from my videos. These are just going to be equal to cosine of alpha, cosine of theta, minus sine of alpha, sine of theta. Again, I proved this in a previous video. You should definitely check it out if you don't know where this comes from. It is very important that you know where it comes from because we use it all the time. And what is the formula for the sine of the sum of two angles? What is the sine of the sum of two angles? It is sine of alpha, cosine of theta, plus this time, and well, it was sine of theta, cosine of alpha. Okay, this is it. All right. Now, when you look at this, I mean, well, maybe if I want to get rid of the parentheses, well, or actually, let's do it like this. Let's write it in a better situation. So, x prime is, as I said, b equals a in magnitude. So, for this b, I can write a. It is a cosine of alpha cosine of theta minus a sine of alpha sine of theta. What is this part? A cosine of alpha. That's x. Let's write that. X cosine of theta. What is this part? That is y. So let's write that. Y sine of theta. Cool. What about y prime? We have a. Again, I replaced b with a. They have the same magnitude. That is the requirement for the rotation that we are dealing with. A sine of theta cosine of, sine of alpha cosine of theta minus a sine of theta. I'm going to write it as cosine of alpha times sine of theta. This is the way that I'm going to write it. Why? Well, because this part is something familiar, isn't it? And this is a plus, excuse me. That's a plus. So again, what is this part? That is y. Y cosine of theta. Plus, this part is x. And then we have sine of theta. I mean, we expressed the coordinates. This is fine. We are done. But we want it in a more compact way. So let's write it as a matrix. And the way to do it is, do I need a new page? I think I do. Let's open a new page. Okay, and here we go. So, what is the result? X prime is, let's quickly copy them. Okay, I'm going to stop talking and just write it very quickly, hopefully. So, and then y prime is, I think it was, yes, it was x sine of theta plus y cosine of theta. I just changed the places of the two terms. We can do that in an addition. Okay. Now, how do we write this? Well, we had the matrix. This is 2 by 2. We have x and y. This is going to equal x prime, y prime. If this is 2 by 2, and as we discussed, it is 2 by 2, it is going to have, it's going to have 4 elements in it. 1, 2, 3, 4. It's going to have 4 elements in it. And this is the rotation matrix that we discussed. This is r theta, this is A, this is B. So, I mean, how do we write it? Well, if you know a little bit of linear algebra, and if you don't know it, don't worry, this is just extra knowledge for you. While multiplying two matrices, what you're going to do is, you take the first row, you kind of put it on top of the first column, you multiply the corresponding elements, and then you add up all the multiplications to give you this value. So basically we want to have cosine of theta here and minus sine of theta here. Because if we have this, we are going to multiply x with cosine of theta, then a plus, we're going to multiply y with negative sine of theta, then a plus, and that's it. And that gives you this, which equals this. Okay? And then for the second row, we're going to have sine of theta and then cosine of theta. And again, here we're going to multiply this with this plus the multiplication of this with this. Then it gives us this. Okay? This is how you can summarize the result in a rotation matrix. And last but not least, I always talk about the other case, the second case. If we were to, like this, if we were to transform the coordinate system, not the vector, by theta, this is x hat, this is x prime hat, y prime hat, y hat, and we have A, let's say. If I were to do this, then the matrix would be, and I can prove this in a future video if you want, please write that in the comment section. It would be this. As you can see, I was kind of right in making sure that you understood that the two scenarios were different because these two results are very similar, but they represent different cases, okay? And let's erase this so that we don't get confused with what it is. Okay, this is it. I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.